Welcome to Linear Algebra, Section 1.1. This is just simply a review of what you learned in pre-calculus when you learned about systems of equations. Some of you may have learned it in college algebra as well. So, what we have, I'm going to start with a 2 by 2 system, very familiar, or it should be, where these are linear equations, so x and y are just to the first power. And what this represents is two lines on a plane. And as long as the lines are not parallel or the exact same line, then there is a unique solution to this system. In other words, there is one point on the plane where these two lines will intersect each other. Now, when you were in pre-calculus or college algebra, you learned many methods to solve a system. One method was to graph, but if the intersection is at the point, say, 5/17 and -19/17, graphing's not going to do us any good, now is it? And many of you are going into some sort of programming. So I want to skip over the graphical method, and I even want to skip over the substitution method, since linear algebra is all about matrices and utilizing them to make everything easier. We're going to focus just on the elimination method. Some textbooks call it the addition method, but the elimination method is the same method that you're going to use to manipulate a matrix to put it in the form that you're looking for, that you can use. So to solve this system by elimination, you want to first choose the variable to eliminate. You then want to multiply one or both equations by whatever number scalar multiple is necessary to get equal and opposite coefficients. So you want the same coefficient, but you want opposite signs. The reason that we want opposite signs is that we never, ever, ever add. We never subtract. We always change the sign and add. We're going to focus on combining instead of just adding or subtracting, okay? So once we multiply one or both equations by whatever number is necessary to get one of the coefficients of one of the variables to be the same number but the opposite sign, then we can combine the equations to eliminate a variable. Combine to eliminate that variable. Once we've done that, if all we're doing is solving a system, then we can back substitute to get the answer. As we start using more and more matrix methods, we're going to keep going. We're going to go farther than just back substitution, but it's a good place to start. So back substitute, substitute, substitute. Yeah, this is what happens when I try to talk and write at the same time. So expect mistakes. Substitute to solve. Okay, so rules. Always write everything down. your busy work, what you intend to do, and I'm going to give you matrix notation to do that with. So, because I said I have to write everything down, the first thing I'm going to write down is what I intend to do. Now, in this particular system, the 3 and the 1, that's easy. I can multiply by a -3 on this equation and combining and eliminate the y. But notice that the x, this is already a negative. Now, some teachers will teach you that you can't get a 0 in the first column first. And I'm sorry, you might hear some background noise. It's just getting really hot in this little recording studio that I call a Nissan Altima. So here we go. I had to open the door. I'm going to eliminate the x simply because it's the easiest thing to do. So eliminate x. How am I going to do that? I'm going to take row 1, that's the top line. I'm going to multiply it by 2 and combine that with row 2. Now, when we're doing this with a matrix, we'll do that, get a new equation, and replace one of the original equations with that in our matrix. So our matrix would always have the same number of rows as what we started with. So now, rule number 1 and all is to write everything down. So I'm going to write down my busy work. I'm going to take the scalar of 2 and multiply the top row by it. I'm going to get -2x, 6y. Don't forget the dude on the other side of the equal sign. He always gets forgotten. Don't be mean, all right? So 2x plus y, the second row stays the same. Now I combine those two rows, I get no x's. That's why it's called elimination. I get 7y's equals 13, divide, I get y equals 13 over 7. Okay, so that's my answer to my first part, 13 over 7. You think you could solve for that by graphing? I don't think so. So I've solved for y. Now I need to figure out what x is. And I can choose either one of those rows to do this because I'm going to get the same answer either way because it's a system and we're solving for the point of intersection. By the way, I said this was a point, so my answer has to be written as an ordered pair. Just keep that in mind. So I'm going to choose number 1 because it has no number coefficient. It doesn't matter. You can choose whatever you want. I'm going to have 3 times y, just substituting the value of y in, negative x plus 39/7. I shouldn't have to go slow with the arithmetic, so bear with me here. Minus x is going to be 7 is 49/7. I'm going to subtract 39/7. That's going to give me 10 over 7. Positive x equals negative 10/7. And I have the answer is the point of intersection of these two lines on the plane. Now, how do you check your work? You plug it back in, right? So I'm going to do a little checking and then I'm going to erase it so you can't see it later on when you look at the notes. All right, so I'm plugging in these two numbers into the original equation. I'm going to do it really small in, hold the phone. I'm going to do it really small in red. What was that? Minus 10 and 13, all over 7. So this is all over 7, negative 10 with a minus sign, and a positive 13 times 3 gives me a positive 49 over 7, which equals 7. That checks. The second one, remember everybody's over 7, so I don't have to sweat the common denominator. Negative 10 times 2, and then I have a positive 13. That's going to give me a negative 7 over 7, which equals negative 1. Both of them check, and I did an amazing job. Except my iPad is now not obeying me. Okay, so you see that when you have the common denominator in your answers, the checking isn't that bad. So always check your answers. You have no excuses for getting the wrong answer. And it's just math, right? It's just arithmetic. So stop whining. Good? All right, next example. Let's say in this case, I have 3 planes, and I want to find the point where the 3 planes intersect. I'm going to use a little bit of different notation. Instead of X, Y, and Z, let's say these aren't planes. Let's say this is something that represents, say, traffic at an intersection or something like that, where the X1, X2, and X3 are things like the day of the week or the time of day or the weather. Time of day would take care of whether the sun is in your eyes at an intersection or something. But if it's raining, you may have worse traffic. Just throwing that example out there. A system of 3 by 3 can also be used to find if you have 3 points on a parabola, for instance. You can find the coefficients of the 3 different powers of x just by plugging in the x values and the y values into some generic quadratic. Oh, I'm thinking I might have wrote the problem down wrong because I got nope, this is correct. Okay, here we go. Process of elimination. In this case, we have to pick what we want to eliminate. That's still step 1. But step 2 is I have to eliminate that variable in 2 different ways. This is very important. If I eliminate the variable 2 different ways, that gives me now 2 brand new equations that only have the other 2 variables. So you get a 2 by 2 system, which is easy to solve. We just did it. You do that in 3 steps. So solving a 3 by 3 system is done in 5 steps, right? You eliminate the variable, you eliminate the same variable again. That gives you a new system. So you're going to eliminate another variable, eliminate a second variable using the previous answers. And then you back substitute twice. Because when you eliminate substitute, is that how you spell substitute? So you're going to back substitute twice. So you eliminate one of the variables, you eliminate that same variable again, that gives you a 2 by 2 system. You do the process that we did before, you eliminate one more variable, that gives you a single variable. You back substitute it into the previous set, and that gives you your second answer. Then you back substitute into the original, pick one of them, any of them, you should get the same answer in all 3. And so 5 steps for the process of elimination here. So I'm going to be very wise about how I pick my variable because I'm lazy. In reality, you can work every problem the same way. I can choose to eliminate x3 um, in this row and this row. However, I could do whatever I want to do. I could multiply all three lines to make my variables negative 29 over 14 if I wanted. That would be dumb because it would be hard, but I can do that. And if I was programming my computer to do this, I would want to do it the same way every time. And when we get to 1.2, we're going to be using matrices, and we're going to use something called Gauss-Jordan elimination. And we're going to get our matrices in specific forms so that then we can then eliminate everything except for our answers. It's really, really super cool. There's lots of really cool things you can do with a matrix to do things like solving systems. So let's get going here. I want to pick a variable, and I'm lazy, so I want to be wise. So I'm looking for ones, or I'm looking for multiples, or I'm looking for something that's the opposite sign of everything else. In this case, I have a 1 in the x, but all of these are positive. For the x2's, I've got a positive and two negatives, so it wouldn't be that difficult. I just multiply by whatever gets the least common multiple. This would be a 12. This would be a 44. No big deal. But I would have to multiply by 11. If I look at the x3's, I have one negative, and the other two guys are positive. My numbers are small. It's not a big deal. I want to eliminate x3 just because it's the day of the week that it is. So I choose to do that. So I'm going to write down what I do. I'm going to eliminate x3 twice. What two ways am I going to do that? Well, grouping row 1 and row 2 together, my least common multiple is 6. So I want to multiply row 1 by 3 and row 2 by 2. So 3 row 1's combined with 2 row 2's. Okay? The next thing that I want to do, I got to pick two different rows. I could do the 2 and the 4 and just multiply by a minus 2 here, but I'm always screw up my minus signs, and you can do whatever you want. I choose to do the opposite signs here. So I multiply him by a 4, him by a 3. Why are they both guys? I don't know. I'm saying him now. So this is a 12, and this will be a 12, and I'll combine them because they're opposite signs. It will go away. So I want 4 row 2's and 3 row 3's. So I'm always going to write down my busy work. So let's do the first things first. 3 row 1's is 15x1's, negative 9x2's, positive 6x3's, and that's going to equal a 9. Don't forget the guy on the right-hand side of the equal sign. You're multiplying both sides of the equal sign so that you're not changing the value of anything. You're still keeping equality. So next step is to multiply row 2 by 2. So I have 4x1's, 8x2's, and negative 6x3's, and it's going to equal 14. If you choose to multiply by a negative because you think that will shorten the problem, go for it. Just be super careful. I am very not careful with my minuses. You'll see that this semester. Minus x2, x3's are gone, and I get 9 and 4, I hate 9s, 23. There we go. All right, next step. 4 row 2's gives me 8x1's, 16x2's, negative 6x3's, and 4 times 7 is 28. Multiplying row 3 by 3, I have 3x1's minus 33x2's, positive, what happened here? I found my mistake. How did I know I made a mistake? Because when I multiply this guy by 3, I get a 12. I was multiplying by 4 here. That was supposed to be 12. So I caught my mistake, learned how to do the same thing. Doing it right the first time is great, but being able to catch yourself in a mistake is even better. All right, what was I multiplying by? 3, so that gives me a 9. I am definitely going to have to check my work. 11x1s negative 33 minus 16 is going to be 17x2s, and adding 28 and 9 gives me 37. Okay, let me double check here. Yep, I'm good. Now, what does that mean? It means that I now have a brand new system from the answers to the previous step. This is god awful ugly. And I'm going to multiply by a minus. Because I see, instead of multiplying by 19 and 11, I'm just going to multiply this guy by negative 17. Yep, I'm going to multiply by a minus. So, minus 17 row 1 combined with row 2. And then we'll be off to the races here. You can't see me, so you don't know that I'm cheating and using a calculator here. So, what do I have to do? I got to multiply 17 times 19. And I'm, this is horrible. Negative 17, right? Negative 323x1. Hey, the real world is very messy. Positive 17x2 and a negative 17 times 23 is 391, except I think I punched a button wrong. Row 2 stays the same. Boy, I hope this works. 37. Let's check it. Those go away. I'm left with just x1s. I'm stalling now. Negative 323 minus 11 gives me minus 312, and negative 391 minus 37 gives me minus 354. I might have to erase this entire page. Minus divided by minus is a plus. 354 over 312, and that can be reduced. All right, 6, they're both even, they're both divisible by 3. So 6 goes into both of these and gives me 59 over 52. Now, that's ugly, but guess what? The world is a little bit ugly and messy. So, we're going to take that value now and back substitute it. And I want to back substitute it into the easiest thing to do. So I choose to back substitute it into this equation. That makes it easy to solve for x2. So here we go. Sorry. Here we go. 19. Start up here. 19 times x1 is 59 over 52 minus x2 equals 23. All right, so I need to multiply 19 times 59, and then this is 1121 over 52. And I'm going to need a common denominator, so I'm going to multiply 23 times 52, and that's going to give me 1196. So x2 is going to equal 1121 minus 1196. Everybody's over 52. Once we get that, we'll see if we can reduce it. So I have 1121 minus 1196 equals negative 75 over 52. Now 52 is 4 times 13. Neither 4 nor 13 go into 75, so that is reduced to lowest terms. So here's my x2 value. Down here is my x1. And now I'm going to pick an equation from the original problem to plug both of those values in to get the third value. And it looks to me like the top row is pretty easy, so that's what I'm going to go for here. So I'm going to have 5 times x1, which is 59 over 52, minus 3 times x2, which is negative 75 over 52, plus twice x3 equals 3. So I'm going to have to multiply out my denominators, and I'm going to have to get a common denominator with the 3, but then I'm going to have to divide away the 2. So here we go. 59 times 5 gives me 295 over 52. And then minus in the times a minus is a plus. 3 times 75, I should be able to do that in my head, but you don't want me to. Believe me. I make enough mistakes with the calculator. Plus that equals, I want to get this over 52, and 3 times 52 is 156. So, x3 will equal, I got to divide away the 2. I'll reduce later if I can. This is 104 in the bottom, and I'm going to have 156 minus 295 minus 225, and I'm going to get a negative 364, which is even. So divide the top and the bottom by 2, and I get another even number. So let's go farther. Let's divide by 4. We said 52 is 4 times 13. So I'm going to just divide by 4. So 104 divided by 4 should be pretty easy. I hit the times. 26 on the bottom. And 364 divided by 4 is 91. Booyah. There is my x3. Now, when you're doing this on paper, you'll have a lot more room than me, so I expect your answers to be pretty neat. So I'm going to check my answer and move on to the next page. All right, one thing that was wrong right here, x3, I forgot my minus sign. And another thing about that reduces to negative 7. So, very cool. 13 goes into both of those. Negative 7 halves, sorry. Yeah, let's mess it up some more, why don't we? All right, 13 goes into 91 is the thing. So we've got minus 7 over 2. What you do is you plug each of those values into the original equation, and you work it out, and you show that all of those statements are true. Okay, so what we saw on the last few pages was how to solve a system of 2x2 or 3x3 variables by the process of elimination. And if we had 2 variables and two equations, we saw that we could get the answer in 3 steps, right? Eliminate a variable, and then back substitute, right? That's 2 steps, isn't it? Then we did a 3 by 3. We had 3 variables, and these, because these make squares, right? 3 by 3, then we should come up with a unique solution if a unique solution exists. Now, if you have 2 lines on a plane, they may be parallel and there's no solution. In that case, you would get a statement that's not true. The x's and the y's would both be eliminated, and we'd have something like 0 equals 5, which is never true. The other situation is if both the same line, in which case the x and y both get eliminated, but we get a true statement like 0 equals 0. In that case, the intersection of the 2 lines is the line itself, because it's one line. Now, when you get to 3 variables, you have the equation of a plane in space. 3 planes sometimes intersect at a point. If you think about where 2 walls come together, they come together in the corner, right? And you get a line through the corner. If you intersect a third plane, like the ceiling, then you see you have 3 lines where each group of 2 intersects, and those 3 lines intersect at the point, which is the exact corner of the two walls and the ceiling. So you can see an example of how 3 planes will intersect at a point. It's also very common for 3 planes to not intersect at a point. You may get a single line, which is kind of cool, where 3 planes all meet at a line. Or you may get 3 planes like that form a triangle, 3 triangular planes where they don't intersect at a unique point. In that case, if they all 3 planes intersect at a line, you would parameterize your answer. I want you to go through section 1.1 and look at the examples in the book. You'll see examples of inconsistent systems and consistent systems with an infinite number of answers and how they parameterize it. I want to get moving on to changing these things into matrices. So writing the first system that we did, writing that in augmented matrix form. Some of you have done this already, some of you have not. So I'm teaching it as new material here. So we have what's called a matrix is just an array of numbers, okay? So we have rows here and here, and we have columns here and here, and I'm going to augment. Your book doesn't augment with a line, it doesn't separate. I want you to separate so you can see. We have a third column right there. The left-hand side is what's called the coefficient matrix. Obviously, we are going to have the coefficients. This is the x column, this is the y column, this is equation 1. I have negative 1 x's, positive 3 y's. Equation 2 has 2 x's and 1 y. Okay? And this is whatever your parameter is on the right-hand side of the equal sign. Now, when we start doing matrix multiplication in 2.1, I'll show you why this makes sense, why this augmented matrix can represent 2 matrices multiplying together, which gives us this system of equations. But for now, I just want you to see how to take a system and write it as an augmented matrix. So the second system that we solved, 5x1 minus 3x2 plus 2x3 is 3. We had 2x1s, 4x2s, negative 3x3s equaled 7. And we had 1x1, negative 11x2s, 4x3s, and that equaled 3. So our matrix representation, we have 3 rows, and we're going to have an x1 column, x2 column, x3 column, and augment that with what those things are equal to. So coefficients of x1 were 5, 2, and 1. The coefficients of x2 were negative 3, 4, and negative 11. And the coefficients of x3 were 2, negative 3, and 4. And these parameters on the right-hand side are the 3, 7, 3. So you see how to convert a system into an augmented matrix. Now remember, your book doesn't have this augmentation line in it. So you have to, if I was you, I'd write in the book. If you have a real book, it's going to be kind of hard to do with the ebook. But when you do your homework, put that augmentation line so you can see what you're doing, okay? So now, the process of elimination that we did before, we didn't care where we got our 0. But when you want to solve a system using a matrix, ultimately our goal is going to be to get what's called the identity matrix on this side with our answers on this side. So the identity matrix will be 1s on the diagonal and 0s everywhere else. We're going to start that process by doing what we did already, eliminating one of the variables, either once for 2 by 2, twice for a 3 by 3, so that we can get 0s either completely above or completely below. Most books teach you to go below. It does not matter to me. Also, most teachers will teach you to get 1s on the diagonal before you do anything else. That means you're going to work the entire problem with fractions. And I know how you love to work with fractions. So my suggestion is you get the 0s first, and then the 1 is easy. It's a simple process to get a 1. You can even wait till the very end to get a 1. Because if I have a 1 right here and 0s here, then me working with these 2 rows isn't going to change that, okay? So it could be a 5 or a 1 or a negative 72. It doesn't matter. I can always wait till the end and divide through by whatever that number is to get my answer. So we are going to go, the book teaches you to get upper or lower row echelon form. In other words, you find the diagonal and you either get 0s completely below or completely above those 3 spots or those 3 spots, and then you back substitute. Because if I get 0s here, then I've solved for z or x3, and I can back substitute twice. But because using a matrix, our goal is the complete identity, we're going to just go straight to Gauss-Jordan elimination instead of getting row echelon form. We'll start with row echelon, but we'll use that answer. All right, you guys don't know what I'm talking about, so let's just get on with it and do it. All right, our goal is the identity. On the left. And that will be augmented with the answers on the right. Okay, the identity matrix. If I'm going to example you here, a 3 by 3. 1's on the diagonal, 0's everywhere else. And this is going to be, I'm going to call this A, B, C, just so you can see what this means. Read row 1. This is 1x1, No x02s, no x3s. So writing this answer down says x1 equals A. You see it? Second row, I don't have an x1, I don't have an x3. All I have is x2, and it equals B. In the same way, row 3 tells me I have one x3 and nothing else, and that equals C. So you see how getting the identity matrix on the left-hand side, we've already done half the work. We just complete it. Once we get that, the rest is going to be easy. And as we do the busy work, you'll see that we get some of the same numbers that we had before. But remember, the goal is to get the identity on the left using the same processes and the same notation that we used when we were just solving a system. All right, so let's make this small, get it out of the way. We're going to do the, let's do the 2 by 2 that we started with first, okay? We had a -1, 3, a 2, 1, and it was augmented with 7 and 1. Okay, that was a -1. Be careful writing things down, guys. Excuse me. So I want to eliminate one of the variables. It looks to me like the x is the easiest, and it doesn't matter, x or y. We're going to either get zeros above the diagonal or below. I'm going to choose to do below. That means I want to get a 0 right here. So I'm going to eliminate an x value and replace row 2. So the same notation, the same busy work that we did before. I'm going to multiply row 1 by 2, combine it with row 2. But the difference between doing what we did before and doing what we're doing now is that we're going to replace one of the rows. And because I want to get zeros below the diagonal, I'm going to get the 0 in the x column, right? So I want the 0 to be in row 2. So I'm going to write down that I'm replacing row 2. I'm also going to write down my busy work. Twice row 1 is -2, 6 augmented with 14. And then copying row 2 the same as it is. This is going to give me a 0 and a 7 and a 13. And I'm going to replace row 2 and rewrite my matrix. My new row 2 is what I just found. Row 1 didn't change. All right, now I can divide by the 7 at this point if I want. That's fine. If you divide by the 7 for row 2, you're going to get 13 over 7 here. And then you'll have to eliminate that 3, right? Because we're going for the identity, which will be 1s on the diagonal and 0s everywhere else. So I choose to leave it the way it is. I'm going to multiply this guy by a -7 and this guy by a 3, and then I'll just get my 1s at the end instead of getting 1s at the beginning. Remember, fractions, they're like your mother-in-law. If you have to work with them, you love them to death, but if you can put it off or avoid it, that's even better. Some of you know exactly what I'm talking about. I did not say that out loud, and this is not recorded, is it? Yeah, fractions are your mother-in-law. Okay, so -7 row 1, +3 row 2, and I want my 0 to be in the top row, so I replace row 1. And I always write down my busy work, so I'm going to get a +7, a +21, augmented with a -49. That's multiplying row 1 by -7. Multiplying row 2 by 3, 0 times anything is still 0, and that comes in handy. That's why this works. Oh, by the way, I multiplied by a minus. Caught myself again. Okay, 3 times 13 is 39. When I combine these, I get a 7, 0, -10. That is my new row 1. So my new matrix is 7, 0, 0, 7, augmented with a -10 and a 13. And I'm going to now divide row 1 by 7 and replace row 1. I'm going to divide row 2 by 7 and replace row 2. If you look at the examples in the book, you'll see a whole lot more fractions. That's because most books and most teachers, they go for the ones first and they end up having to deal with nasty numbers all the way through the problem. So I like to wait until the last step to get the ones. And it's the difference between dividing through by the 7 here and then eliminating this by multiplying by a -3, but then you're adding fractions here. I multiplied twice and dealt with whole numbers and did the division at the end. So 6 of one, half a dozen of the other. You do it how you choose, but now I have created the identity matrix on the left, and I have a -10/7 and a +13/7. And because we stated that these were two lines on the plane, I can see that 1x plus no y's equals -10/7, and no x's, 1y equals 13/7. And that's the point of intersection of those two lines using Gauss-Jordan elimination on a matrix. Now let's do a 3 by 3. Now, the system of equations that we had before, and we've already written it as a matrix, so we're going to go straight there. X1 had coefficients of 5, 2, and 1. X2 was -3, 4, -11. We're going to get big numbers here, guys. A 2, a -3, and a 4, augmented with 3. I get so lazy I don't even do the dots anymore. Join me, won't you? So we want to get, these will eventually be 1s. So we want to get 0s below the diagonal, or we could get 0s above. It doesn't matter. We just have to go for it. So I'm going to choose to eliminate x twice. I'm going to get a 0 here, and then I'm going to get a 0 here. Getting 2 0s in the same column leaves you with a 2 by 2 matrix, which makes life so much easier. So once we get these 0s, we can use these two numbers to get that third 0, and then we'll have lower echelon form. We will have solved for the third variable. We can use this guy right here to eliminate him, and then this guy will be the only guy left, and we'll use him to get a 0 here. It's beautiful the way it works, and if you're programming a computer to do your matrix manipulation for you, it's just easy. You get a 0 in row 2, row 2, column 1, get a 0 in row 3, column 1. That gives you a stack. Then you're going to get a 0 in row 3, column 2. Then you're going to use row 3, column 3 to get a 0 in row 2, column 3, and row 1, column, and use 2, 2 to get this right here. We'll talk about the notation that I'm using in my words soon. Okay, so, all right, always write down your busy work and what you intend to do. So using rows 1 and 2 to eliminate and get a 0 right here. It's easy, hard, whatever, it doesn't matter. I'm going to multiply 2 row 1s and 5 row 2s. I want one of them to be negative. I don't like to think about subtraction. You can put the minus where you want. You'll get the opposite, but that doesn't really matter. I'm going to use this to replace row 2. Then I'm going to use row 1 and row 3. So row 1 and 5 row 3's, a minus and a plus to get the signs opposite, replace row 3. So busy work first. -2 row 1 gives me -10. I'm going to do this in a different color here, just to keep the real work and the busy work separated here. Let's use a calming blue here. -2 row 1's gives me -10, +6, -4, and a -6. Now, check my work. I multiplied through by a minus, so I should get a minus, a plus, a minus, and a minus. That's what I got. Doubling everything gives me a 10, a 6, a 4, and a 6. Boom, I did it. Now let's do 5 times row 2 is going to be a +10, a 20, a -15, and a positive, what was I doing? 5s, 35. Check my work. I multiplied by a 5, so this is a 10, 20, -15, +35. Yes, that's what I got. It's so easy to make a little teeny tiny mistake, like copying something down wrong, and it screws up the entire problem. So you always check when you copy things down. So here we go. Adding, I get 26, -19. These are ugly. And a positive 29. Now, we're replacing row 2 with that. Notice that we're replacing rows 2 and 3. So row 1 stays the same. So I'm going to just go back and write what we have so far. Row 1 stays the same, being very careful with my minuses. My new row 2 is 0, 26, -19, +29. And now I'm going to go back and do the busy work to replace row 3. Now, a lot of the books and a lot of the teachers would copy row 3 down the way it is here, put it right here, and then do this step separately. But you see I replaced row 2 and now I'm using rows 1 and 3, so it doesn't really matter. I can do both things at once. So I'm going to do negative row 1, which is going to be -5, +3, -2, -3, and 5 row 3's, which is going to give me a +5, -55. 5 times 4 is 20. 5 times 3 is 15. I'm going to combine these and get -52, which looks right since we've done this already. +18 and a +12. That is my new row 3. Wait just a second. You see that these are all even numbers. So before I put that in there, I'm going to say row 3 divided by 2. Make my numbers smaller and easier to work with. You're dividing both sides of the equal sign by 2, so you're not changing the value of anything, right? So I'm going to get a 0, a -26, +9, and a 6. That's my new row 3. 0, and look at that beautiful situation we have here, where now the next step would be, we've got the stack of zeros. We're going to use these 2 rows now to get another 0 right here. And look, all I have to do is add. So my next step is row 2 plus row 3. And I want that 0 to be on the bottom row. So I'm going to replace row 3. I'm not going to break the rules. I'm going to write down the busy work, although it's easy. -26, +9, and a 6. When I combine, I get 0, 0, which is what I wanted. negative 10, and a 35. Notice that both of those are divisible by 5. So I'm going to keep going, divide by 5, and replace row 3, and that's going to give me now this beautiful, here's row 1. We haven't done anything with him yet except use him. Row 2 is 0, 26, negative 19, 29. But now my new row 3 is 0. I divided by 5. 0 divided by anything is still 0. Now minus 10 divided by 5 is minus 2. And this divided by 5 is 7. So those are my two answers here. And I have a lawnmower behind me. Sorry for the noise. So you see, if I back substituted at this point, I would have that my x3 equals negative 7 halves. We've worked the problem before, we know that's correct. So what I choose to do though is wait and get my ones later so that I don't have to deal with so many zeros. And the goal is to get the complete identity matrix. So in the end, we'll make ones on the diagonal, but I got to get these guys to be zeros. So this has two zeros here. I can use this guy to get rid of this guy. And that's going to leave me with just the x2 value in that row. Okay, so I'm going to switch colors for my busy work so I don't get mixed up here. What I need to do is get opposite sign, same number here. So I choose to multiply row 2 by 2, and I'm going to make it negative. And I'm going to multiply row 3 by 19. And I want that 0 to be in row 2. Sorry, row 2. Okay, busy work now in green. Negative 2 row 2's is 0, minus 52, positive 38, multiplying by a negative 2, I get a 58. 19 row 2's, 0, 0, that was easy, negative 38, which is what I wanted, and now 7 times 19 is going to be 70 and 63, 133, and it's positive. I hope. 0, negative 52, 0, which is what we were going for, and now 133 minus 58, cheating with the calculator here. 133 minus 58 is 75, positive, and that looks right. So you can see that if I divided, I would get x2 equals negative 75 over 52, which is what we got before, right? But in this case, I'm just replacing row 2 with that. And I can divide through whenever I want. And maybe I'll do it now. Let's just write down what we have here. Boy, whew, what a mess. 5 minus 3, 2, 3, 0, negative 52, 0, 75. There's my replaced row 2. Row 3 was 0, 0, minus 2, and 7. So now let's go ahead and get ones on those two. So row 2 divided by minus 52, replacing row 2. Oh, I'm going to have to make this smaller and give myself more room, huh? Row 3 divided by minus 2, replacing row 3. So my new matrix, 5, negative 3, 2, augmented with 3, 0, 1, 0, 0, 0, 1. Row 2, I get minus 75 over 52. Row 3, I get negative 7 halves. So now you see that it's two more simple steps. I'm going to multiply this by -2 and add it here. I'm going to multiply this by 3 and add it here. And then I'll divide through by a 5 at the end. So let's write all that stuff down. Row 2 gets multiplied by a +3 combined with row 1. And row 3 gets multiplied by a -2 and added to row 1. And all of these are going to replace row 1. And then I'm going to take row 1 and divide by the 5 to replace row 1. All right, making this smaller, if I can figure out how. Oh, very good. Okay, busy work. I'll do in a different color. Stick with the green here. So 3 row 2 is going to be 0, 3, 0. 3/75 is 225, -225 over 52. And that is getting combined with row 1. This should be in order. Sorry. 3 times 52 is 156. Just getting a common denominator there. That's going to leave me with 502. And 156 minus 225. I'm just combining these numbers right here to get -69 over 52. Okay, so that's my new row 1, but I'm going to also do the second step. Sorry, I'm having to combine steps here. If we were in a classroom, I'd be using like 5 whiteboards right now. I'm going to take row 3 and multiply by -2 and add it to what I just got. And I can do that in one step here. So -2 row 3's is 0, 0, -2. -2 times -7/2 is going to be 7. Get a common denominator. 7 times 52 is 364. And I'm combining it with what I just did, okay? So 5 and 0, 0 and 0, -2 and +2, and now 364 minus 69 is going to give me 295 over 52. So I'm going to now divide that by 5. So 359 divided by 5 is 59, 395, sorry, over 52. That's my new row 1. So rewriting the entire system now, row 1 is 100 augmented with 59 over 52. Row 2, copy it down from before, 010 with a -75 over 52. Row 3 is 001, -7 over 2. That is the identity matrix on the left, and you see that x1 equals 59 over 52, x2 equals -75 over 52, and x3 equals -7/2. And that's the same answer that we got when we worked it before. X1 equals 59. X2 is -75. And x3 is -7. over 2. Da, 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 da. I know that that was very nasty with lots of big numbers. You don't always get the big nasty numbers, but yeah, sometimes you do. Just you're doing all your work at home, so obviously you're allowed to use a calculator. I really, really, really expect you guys to do the work by yourself, though. Don't just use an app or a spreadsheet or something. You're going to need to be able to whip out that arithmetic pretty quickly and accurately. So practice, practice, and practice. Okay? So that gets us pretty deep into 1.2. You're just solving a system of equations with Gauss-Jordan elimination. When you text me with any homework questions that you might have, and we didn't even know we were doing 1.2 yet, did we? Text me with any questions you might have, and or take pictures of your homework questions if you get stuck. Text the pictures to me. I may work it out and text you a picture back, or just tell you where your mistake was, or we can jump on Zoom. I'm going to try really hard during daytime to make myself available to you guys so that we can just get together on Zoom whenever you need to. All right, one more page and we're done. Everybody's favorite page here. 1.1 homework is 37 through 55, and you're going to do every other odd. And you will usually see EOO in the assignment. That means do every other odd. In other words, you're going to do 37, you're going to skip 39, you're going to do 41 and skip 43 and work your way through. If you don't end on 55, it doesn't matter. It's just that instead of doing every odd, I want you to just do every fourth problem instead of every second problem. 1.2 is 11 through 23, every other odd. 25 through 37 odd. And there's one more video to come in quick succession, and it's all about, because what we just did should be pretty close to review, except for the identity matrix stuff. And then in 1.2, we're going to go over some properties of matrices. We're going to add and subtract. We're going to talk about notation, and then we're going to learn how to multiply, which is a little bit messy and complicated, but I know you'll get it. Okay? Do homework.